Hello everyone, good morning. My name is Anurag and I am from the Department of Computer Science and Engineering, Government College of Engineering and Textile Technology, Shirampur. Today in the IET Regionals, my problem statement that I will be presenting on is to ensure affordable and clean energy for healthcare. Firstly, I would like to thank IET for allowing me to present my idea at the regionals. Secondly, I would like to extend my gratitude towards my college. Without their support, I won't have been able to make this far. Starting with the introduction, as I mentioned, the objective is to ensure economically and environmentally viable energy for the healthcare sectors. Now, the suggestion that I want to put forward is to make use of predictive solar power usage in the hospitals, and that we will be doing by making use of physics informed neural networks in predicting the solar power at a particular time step ahead window, and using that we will be able to have some prior information about the potential of the solar energy magnitudically throughout that window. Now obviously the demand for fossil fuel based energy, that is the ones that we get from coal, petroleum and all, cannot be disregarded completely but can be minimized by a larger factors. So the motto of this presentation is to make fossil fuel based energy a backup rather than a necessity. The technological stack that we are going to make use of in this presentation are artificial intelligence and chaos theory. Now, from this slide onwards, we will be presenting the preliminaries of the proposition. So, the very first preliminary is van der Waals system, which is a non-conservative self-oscillatory system with a non-linear damping constant, which have been represented by the Greek letter mu, and the corresponding second order differential equation is as in equation 1. Now, Mahmood and Farghali in their work have shown that the maximal Lyapunov exponent of a van der Waals system is 0.09, which is obviously greater than 0. And it's known that if any system is having lambda max, that is the maximal Lyapunov exponent, as greater than 0, then that is chaotic in nature. So, from this, we can say that the van der Waals oscillator is also chaotic in nature. Now, the solar energy attainable at any given location will vary on a lot of reasons, like the climatic fluctuations are there, the radiation level that is available in that region, the pollution level, everything have a impact on the solar energy that is attainable at that region. But climatic fluctuations will have a major role or a crucial role in this. And Van der Waals system have been known to model this chaoticity well. Next comes the second preliminary, that is long short-term memory, which is a neural network consisting of three major components. One is this input, output, and the other one is this forget get. Now, before discussing about the LSTM block or the LSTM architecture, I am going to take use of an example. So, let's say we are reading a novel, Tom Sawyer, let's say, and we have one chapter in which it's mentioned about a new adventure of Tom Sawyer. Now, the context of the new adventure in this chapter may be required as a citation or reference in the next chapter, but not maybe 5 chapters ahead. It won't be like that. But if someone wants to have knowledge about the personality of Tom Sawyer throughout the chapter, then he needs to have a close, keen look on how Tom Sawyer's personality and his characteristics are changing through the course of time throughout the adventures that is going through and all this. So the entire context of any novel can be divided into two parts. One is the short term memory and the other one is the long term memory. Similar to that, LSTM considers these two things. One is this long term memory, which have been represented by CT minus 1, and a short term memory, which have been represented by HT minus 1. Now, definitely, they will be having some forgetting mechanism, because of which they are going to remove some portion of the memory from the long term aspect so that it can minimize the weightage on the memory part, obviously, and then it will be saving some portion from the long term memory for the next unit of the LSTM. Now there will be some kind of computation going on, some operations going on, like this. There's the scaling operator, which is like a cross inside a circle. This is the information scaling operator. Then we have the information addition operator, which simply adds to information and pushes on to the next thing, onto the output actually. So As an output from this single LSTM unit, it gives another CT and HT, which are the long term and short term memory respectively, which are passed on to the next LSTM block. Now, LSTM have been widely employed in various sequential tasks like natural language processing, machine translation, image captioning, and time series forecasting. For the context of the proposition that have been laid in this presentation, we are going to take care of time series analysis by LSTM as a benchmark kind of thing, as a skeletal benchmark kind of thing. This comes the proposition that we are going to present in this, that I'm going to present through this presentation. This proposition is named as Van der Pol Informed Neural Network for Multi-Step Ahead Forecasting of Extreme Climatic Event. This is from one of our latest poster presentations at the NIPS 2023. Now, the I will try to discuss about this VPINN structure in detail from this slide onwards. So it have been abbreviated as VPINN. So VPINN utilizes the transfer learning approach and physics based loss function to significantly improve the modeling and forecasting capabilities of the skeletal backbone, that is the LSTM network, which have been used over here. To begin, initially we will be having we will be generating one simulated data of the Van der Pol oscillator, and for that we are going to take mu equals 1, that is the damping constant equals 1, and the initial coordinates as the 2 and 0 respectively. It will definitely generate a time series xt indexed at time t, and then we are going to compute its time derivatives by making use of the very first principle of derivative, which have been represented in equation 2. Now, in accordance to the first principle of derivative, del t that we can see over here will depend upon the context of the problem that we are dealing with. So, if the data set that we are dealing with is a daily frequency data, then definitely del t is going to be 1. If it's a weekly, then it's going to be del t equals 7. Like this, it will vary. Now, initially we will be giving. Acha, one more thing I wanted to mention is this VPNN module consists of two phases. One is this pre-training phase, another one is the training phase. Now, uh, when the pre-training phase is taking place, so in that we will be giving these three things as a tuple. That is the xt, that is the time series generated simulated time series. Then its time derivatives, which will be traversed through in the pre-training phase, wherein based on the simulated data, the weights and biases which have been initialized randomly in the very beginning, they will be updated. And the updation will be done by making use of a physics based loss function L phi, which leads to a predictive tuple. Now, the physics based loss function is computed as in equation 3. It relates the simulated data, its time derivative, and the predicted version of the simulated data and their time derivatives. Now, this accounts for the pre-training phase. In the next phase, that is the training phase, we will be taking in one, we will be taking in one real-time data set X train indexed at time t, wherein the weights and biases will be will be loaded from the uh, pre-training phase, and they will be transferred by making use of the transfer learning approach. And in this phase, the weights and biases, or in general, the parameters will again be updated, but this time it will be done by making use of a data-based loss function, L data, which have been represented as in equation 4. It also relates the real-time input data set, real-time time series data set actually. Now, hereby, for the context of this presentation, we're going to make use of regional solar power data as an input, and definitely it will be having its predicted version, that is x hat train. Now, this image that we can see over here is the architectural view of VPNN. So initially we'll be taking in the Van der Pol system. Now, this figure, as we can see over here, is a 2D representation of the Van der Pol oscillator. So, based on this and the initial conditions that I discussed, I think 2 slides before, it will be generating one simulated data. And by making use of the first principle of derivative, we will be computing its time derivatives, that is dx by dt and d square x by dt square. And this will be forced on to the LSTM units. Now, for the context of this research in VPNN, we considered 50 LSTM units, and it will be then taking on to some back propagation steps, and the loss that we are talking about will be taken in as this two loss functions in different phases, that is the pre-training and the training phase. These two loss functions will be combined together to give a total loss, which will be a linear combination of the data loss and the physics-based loss. Now, compiling these two things, we have made use of some trial and error mechanism, and we got that whenever we gave zero point 0.8 as a weight of the data loss and zero point 0.2 as a weight of the physical loss, we got the best results. Now, even though VPNN have been proved to do well with extreme events dataset, for the experimentation as in context of this presentation, we have considered one solar dataset from the London data store. Now, the source of this data is as can be referred from this link over here, and we got this results as we can see in this table. So these first two rows are corresponding to the very short term forecast, in which he considered 7 days ahead forecast of solar power, and this next two rows are corresponding to the long term forecast, where is considered 20 step ahead forecast. Now here we can see that the very first column corresponds to the, not this one, this is for the matrix, and this second column is corresponding to the proposed model VPINN, and the rest of this are kind of the state of the art model. Again, this KDL is proposed by Professor Tonuji Chakraborty and some of his colleagues from Sorbonne University of Artificial Intelligence (SCAI). So this is also a physics informed neural network. Second one is LSTM, which is definitely the backbone. Then we having the by LSTM, N bits, profit, RC, and this is reservoir computing and SES. So we can see like in most of the cases, VPNN is giving us a better hold on the scenario. Now, since it's evident from the table that VPNN works well with several state-of-the-art models, hospitals can install solar panels with predictive modeling. This would enable them to use solar power, which is both environmentally and economically viable, with predictive modeling capabilities. This would allow them to utilize the solar energy whenever available and get prior information of its magnitude, and also get to know whenever it's going to be disrupted. That may be due to some variable weather patterns. This would further benefit them for sustainable planning and promoting more usage of solar power. Now, fossil fuel based power through electricity generator or from power plants can be considered as a backup, but they should not be a necessity. Recently, this is a screenshot from the Harvard Public Health. They says that the future of healthcare in rural India and elsewhere is going to be solar powered, and that was kind of the motivation behind this proposition that we have laid in this presentation. So this was all about my presentation. These are some of the references that I took help of for preparing the presentation. So thank you once again for being with me throughout the presentation. Every material codes, everything that I have mentioned in this figures, everything that I have mentioned in this presentation can be referred from this QR code. I have also added a few supplementary slides, which are like, this is the 3D plot of van der Waals system with the same initial conditions. Then this is a general architecture of artificial neural network consisting of an input layer, and these are the hidden layers, and there is an output layer. And this is the artificial neural network traversal mechanism, wherein there are some weights and biases attached with it. Also, there is some activation function. So this is it. Now I am open to the question and answer session. Thank you.